High energy. You probably know play part and strong. How long are you in class?
Very good. Let's get the Raphael is going to tell us about more.
Yeah, so yeah, we'll see, I guess, how it goes. So one thing I did want to do in the discussion, because there were some questions, was maybe say a little bit more about the CCWZ. Also because it was kind of cut a little bit short, so maybe just to make sure everyone can actually follow what's going on. And so I won't then talk about it now, I'll do it in the discussions. But if there's any other questions, I guess, let me know now. Otherwise, what I'll do is just a summary of the logic of the effective field theory approach, and then we'll see an application of the approach to describe long string-like objects, because this is what Pedro initially asked me to talk about. So and let me be specific and just put the L here for low energy effective field theory. But really, it's quite similar for the other EFTs. So the starting point, the first thing you want to do is just identify the light degrees of freedom in your system. And by light, I really mean that their masses are lower than the energies I have access to. So I can, in principle, produce them. Everything that's heavier, I can get rid of, as we discussed, because you can't reach the poles or the branch points, branch cuts it gives rise to. The next thing you should do is identify the symmetries of your system. And then what you want to do is just write the most general effective action that you can for these light degrees of freedom that respects the symmetries. And this goes hand in hand with some other things. So you also have to understand the power counting and understand which terms in this action contribute to your observables. And you should probably do these at the same time, roughly, so you're not constructing terms that you're never going to use. And you should also make sure you find a regulator that respects the symmetries, or if you can't find such a regulator, add the appropriate covariant and non-covariant counter terms. To make sure you're satisfying the word identities. Sometimes people forget about this step and then they get results that look interesting, but they're just plain wrong. So don't forget about that step. So these kind of go hand in hand. And then once you have these, what you want to do, or what you can do now, is just work out the predictions of your theory. To the desired precision. And typically these theories will contain a number of free parameters, and depending on what the UV theory looks like, you will either just obtain them from a matching calculation. So if the UV theory is known and calculable, perform a matching calculation. Or if the UV theory is unknown or uncalculable, then just get those coefficients from experiment. And experiment here can also mean you do a lattice calculation. So you can ask Tom, for example, to obtain the C coefficients that I had in the model. Yeah, that's fine. But okay. So are there, I guess, any? Well, yeah. So what I also. So natural ingredients in this thing. You either have scalars that are associated with some spontaneously broken symmetries, and they might just be approximate symmetries. I haven't really discussed how to take that into account in a systematic way, but it can be done. And then, or you can have chiral fermions because their masses are protected by the chiral symmetry. Or we can have things that just can't get a mass because the degree of freedom counting doesn't work unless you have other degrees of freedom around. So massless spin 1 or 2 particles. And what I wanted to do is really show you here that Lorentz invariance for the spin 1 particle is enough so you at low energies get a theory that looks like QED for any massless spin 1 particle, assuming you have charged matter. And for spin 2 particles, similarly, if you write down the most general effective field theory compatible just with Lorentz invariance, you will at low energies get a GR. I'll skip this, but if you want to know a bit more how it works in detail, I'm happy to discuss it, I guess, in private or also in the discussion. And so now the next step I want to do is apply this logic to a long effective string. So we want to derive an effective field theory for long strings. And these long strings really are some string-like defects in field theory. So these could be QCD flux tubes, or they could be cosmic strings. And this is what I'll try to do. So are there any questions about this approach? Any? Yeah?
What are examples of effective field theories that are not low energy?
What are examples of? I mean, there's, for example, non-relative. I mean, it's in some sense maybe still low energy, but you might have non-relativistic field theories. You can even have classical non-relativistic effective field theories that people. You can find some of this in a review that I didn't list, but Walter Goldberger has a review on their theory of black hole in spirals. Where this is an example that's not really literally in this class. The logic is kind of the same, but technically you're expanding in something else. You might be expanding in the velocity, or maybe soft collinear effective field theories are not quite of this form. So there's a number of other effective field theories, and some of them are in the reviews I gave. Any more questions? Okay, so then the first step to identify the light degrees of freedom. So if you have a long string-like object, you might have something that looks like this. So let's call this x1, x2, x3, and then you might have some string-like object here that looks like this, and you might ask how you describe it. So you might describe this thing by its location in the x2 and x3 plane as a function of time and x1, and I'll call the coordinate along this string that's just z equal to x1, I'll call sigma. So this is described by some fields xi of tau and sigma, and you see that by because this object spontaneously breaks the translation invariance, the action cannot really depend on these, but they must appear with derivatives. I mean, if you move this configuration over here, you get something that looks like this, let's say, and these two must have the same energy. So the energy can't really involve the xi's. They must be derivatively coupled. They're our Goldstone bosons. You might ask if there's additional light degrees of freedom that are associated to the broken rotation. So any rotation that involves the x1 direction is also broken. And the answer is that they don't really give rise to independent Goldstone modes, because if you have because this is a space-dependent translation, so you already have space-dependent translations here, so you don't need extra light degrees of freedom for the spontaneously broken rotations or boosts. And we'll also see that this is enough to really construct the Lorentz invariant theory. So these are the light degrees of freedom. And in general, of course, you know that strings have many excitations above the string scale. So there's many stringy excitations if you go to high enough energies. So low, in this case, will mean I'm interested in energies below the string scale. So I will call this the string length. I mean, ls squared, this is alpha prime, I guess. So so I want the energies to be much less than the string scale. Then these are really the only degrees of freedom I have access to. So this is the first step. Does that make sense? Okay, so now what we said is we have to identify the symmetries of the problem. And here the underlying theory so the underlying symmetry, the symmetry of the underlying theory, if we're in d dimensions, was the Poincare group in d dimensions, which I'll write in this way. And then a string that just extends along the one direction, it will break it to the Poincare group along the string. and then the rotations in the transverse plane. So for example, in 3+1 dimensions, so when D is 4, you just have an SO2. This is just the rotations around the string, so in the plane perpendicular to the string. So this is the symmetry breaking pattern, and now we can we're supposed to construct the most general effective action for these guys compatible with this pattern of spontaneous symmetry breaking. And I should maybe say, so in general, you might have additional symmetries in your UV theory. So for example, you might have a supersymmetric field theory. Then here you have the super Poincare group. You might break some of the symmetries, some of the supersymmetries by the presence of this, and then you can you get an effective superstring. So if you have additional symmetries here, you might get additional light degrees of freedom, like the corresponding fermions you need in this case. But in the absence of additional symmetries, really, these are the only light degrees of freedom that you expect. So we construct now an effective action for these. So and there's two approaches that I briefly want to mention. The first one is what has been used most of the time, and this is also what we did in the paper, just because it's easy and convenient. So you can either use you start from the fact that again, near the identity or near the origin, it should just be at very low energies. They should just be a bunch of free particles, and you start from this action and the transformation properties. To construct the effective action order by order. Now, the unbroken symmetries are easy to implement. It just means you want to write down a theory that's Lorentz invariant in 2 dimensions and is SOD minus 2 invariant, which just means that these, which I'll call flavor indices again, that these flavor indices are contracted with each other. So we know that the effective action must be of this form, so it's integral d2 sigma 1/2 d alpha xi d alpha xi plus, and then you can definitely add this term squared, so you might have a C1, and then d alpha xi squared, or you might have another term C2 d alpha xi d beta xi d alpha xj d beta xj. And in terms of vertices, again, I'll write them the way I did for the pions. So this will be the flavor indices, and then I'll have derivatives. In this case, the derivatives and the flavor indices are contracted in the same way. And for this guy, the flavor indices and the derivatives are contracted in opposite ways. So this is what we get from the unbroken symmetries. And then from the broken boosts and rotations, so under these, what you have is that the X is transformed in this way. So you have under these rotations, you get, well, the minus, overall minus, but it doesn't really matter. So there's sigma alpha delta ij plus xi d alpha xj. So this is similar to the nonlinear transformation for the pions. And then you see once you substitute this into your action, this one, this one substituted in here gives you a cubic term. This one and this one, they give you cubic terms from here. So the coefficients C1 and C2 will be related to this one. And in fact, this fixes the coefficients to be C1 minus 1/8 and C2 is 1/4. So let me just put them here because I want to keep that action. And then no, so that it's invariant under this infinitesimal transformation. So I'm saying if you vary the x's in this action by this transformation, then when you plug this guy into this term, it gives you something cubic, and this has to somehow cancel against something, and it cancels against the piece where this one ended up in here. And so it relates the various coefficients, and then obviously there's plus ... and depending on how strong you feel, you can just go to as high order as you want in this. This is one of the ways that people derive the effective actions for these things. The other way is to just use the symmetry breaking pattern and use the CCWZ construction generalized to space-time symmetries. Let's say to include space-time symmetries. And the extension is always attributed to Volkov. I've never been able to access the paper because it's in some obscure Russian journal that I've never had access to, but it's always credited to him, so I'm sure he did this first. And the idea is, or the way you would parameterize the coset in this way, so we can write gamma, so this is some point in the coset. So the only modification in this case is that you have e to the minus I, and then I call them sigma alpha. These are my coordinates on the worldsheet. P alpha, e to the... So these are some of the unbroken generators, but they now appear in the parametrization of the coset. I'll say y in a second. So then I have the xi of sigma pi e to the minus I omega alpha I, or let me call them the other way around, I alpha, I alpha. And this is it. And then the unbroken generators are the rotations generated by Mij, and the boosts generated by M alpha beta. So this is how you parameterize your coset. Then you work out the left invariant one form. And I won't go through the derivation. I have notes on it, so if you want to see it in detail, I'm happy to discuss it, but I don't have time to fit it all in the lecture. So what happens is that you get some minus I. So it has to be proportional to all the generators of your group. I'll just call whatever multiplies my translations in the 1 plus 1 dimensional space by minus E. I'll call them EA for reasons that I'll explain in a second. I'll call these CI, PI, minus I. And then you have these guys, I alpha, M, I alpha. And then there are some pieces, V, IJ. Well, let's put them, well, it doesn't matter. Ij minus I over 2 V alpha beta, M alpha beta. And so the interpretation of this thing is that under a transformation by G, or you move in G mod H by some element in G and do the compensating transformation so you stay in the same slice, this will transform under a Lorentz transformation of the unbroken groups. And it's also a one form. And so this is something that is a Vielbein, and you can use it to write an invariant action. So the leading piece in the action, and let's put in the dimensions. So there's some E0 wedge E1. This is the leading piece. And then you should add all possible things that are invariant under the action of the unbroken group. So certainly 1 is invariant, but you might also add coefficients proportional to these guys. So there's alpha, beta, ki, alpha, beta, plus. So let me call them D's or something because I used C's earlier. So there's a D2, ki, alpha, alpha, ki, alpha, alpha, plus all kinds of higher derivatives. And at leading order, you can convince yourself that these kind of things are kinetic terms for the omegas. Now, people usually say you should impose a inverse Higgs constraint for these omegas. In the effective field theory approach, you don't really have to impose anything. You'll find, if you work it out, that they have a mass coming from here, which is of order the string tension. And so if you're interested in energies below the string tension, you can integrate them out. And effectively, this amounts to setting the Ci out these W's. And this is what people call the inverse Higgs constraint. What it does is it equates this guy with, after you integrate it out, you find that this guy looks like this. And this is the extrinsic curvature of the string for this embedding. And you also find, there's also a minus sign, I guess, if one wants to get the signs right. Yeah? Yeah, so here it was still a one form. The Ki alpha is a one form. And I'm saying Ki alpha is Ki alpha gamma d sigma gamma. And so it's this guy. And then also I'm not super careful, so you should be a bit careful how the indices are contracted. So some of these you want to use the Vielbein for them to make sure they're contracted in the right ways. Because, for example, or you just can say you contract this one with the induced metric. It's the same thing. But yeah, so what you get after you integrate this thing out, you can show that this piece is just minus the determinant. Yeah, sorry. This is just the Nambu-Godo piece. It's really the invariant volume here. And then you have additional pieces that you might add, these extrinsic curvature pieces, D1, Ki alpha beta, Ki alpha beta, plus D2, Ki alpha alpha, Ki, well, let's just call it squared, plus dot, dot, dot. So this is what you get from the coset construction. And if you expand it out, you get the same thing, except here I'm also including terms that I could have included there too, where you have more derivatives acting on the axis. And one more thing I want to say is that there is a relation from differential geometry that relates these two extrinsic curvature pieces to the intrinsic curvature. So these are related to the Ricci scalar and by the so-called Gauss-Codazzi equation. So you can get rid of this in favor of this, and in 2 dimensions, you know this is a total derivative. So you can ignore this one if you like, and just keep this one. And then this one you can actually also get rid of, because you can see that in general this is proportional to the equations of motion, to the lower order equations of motion. So if we're doing an expansion in the number of derivatives minus fields, or then this guy is higher order, and it's actually a redundant operator. So this is why I briefly went through the exercise of redundant operators. And the simplest way to make this plausible, at least, is for me to remind you that the extrinsic curvature looks like this. So at leading order, this is just d alpha xi, which is just the leading order equation you get from our action. So you can remove this guy by a field redefinition. Yeah?
Just from the point of view of the symmetry argument, how should the action know that it was a single string breaking this symmetry and not like a stack of strings all doing the same thing breaking this symmetry?
Well, I think at leading order, at low energies, it's really the same. And then you would have, if you have bound states of these things, so assuming that it's forming a bound state, your n strings, you will then see excitations that you have access to. So this effective field theory will break at relatively low energies. This is something one actually sees in the lattice data, where they can look at bound states of flux tubes. And if you look in the sector where you have bound states, you see that you actually have a breathing mode that you can excite at relatively low energies. So you can still do this, but it breaks down at relatively low energies, and then you have to, if you want, include the degrees of freedom that describe the rest of the motion. Yeah?
I have one dumb question. Before, when you were doing just the symmetry argument, you ended up with some sort of space-time action.
Mm-hmm.
Now you seem to be ending up with a worldsheet action.
This also a worldsheet action.
So does the symmetry argument itself tell you what the space or where you put that in?
In what sense? So I only get coordinates for my unbroken generators, if you want. So, and here the point was, I guess, I don't know if the little picture is still there, but really to specify the string, you only had to specify the position in the transverse plane as a function of time and x1. So this is assuming that you don't have a crazy embedding, that this actually makes sense. I mean, these coordinates don't globally make sense necessarily, but locally at least this is the reason why it only depends on those two. You can also, you can also actually see it from some of the general arguments for Goldstone bosons I made, but I didn't have time to really explain it better. But you can see that they really only propagate along the string, these modes. Yeah? Why the unbroken generators are present here in the one form? Yeah, in the one form, it just always so happens. I mean, this also happened for the pions, and these play the role of the connection. So if I actually had some other states, some other degrees of freedom that I wanted to couple, so for example, if I had an SO2 vector that I wanted to put on the worldsheet of the string, this Vij would be the corresponding connection that you need to make so what you would write then, let's call that guy, let's say you have some field chi that you want to introduce on the worldsheet of the string, then you should introduce derivative, covariant derivative for this guy, and then it minus I/2 Vij alpha. So this was also one form, so it gets the alpha mij. This is in the corresponding representation. So this is d of mij. And now my indices are horrible, so let's. So this is KL, and then I have IJ here, and J, and then I have delta IJ here. So it would play the role of the connection that you need to make the action for this guy invariant under the nonlinearly realized symmetries. And similarly, if you had something that's a worldsheet vector or whatever you want to put, you would need this connection. Yeah? Is that range empty? No, LS is some fixed scale. Sorry, LS is not really the length of the string. It's related to the string tension. So it's the thing in front of the action. So it's some fixed scale that characterizes your scale, your string. So in QCD, it would be related to the QCD scale. In string theory, it's the string scale. So it's some fixed scale that sets the masses of the massive excitations of the string. So it's not the length. In particular, I'm working in the regime, if you call the length of the string LS, R, then I'm working in the regime where R is much bigger than LS. And then also because the energies of these guys, you can already see now from this action, they will go like 1 over R squared integrated over the string, so they go like 1 over R. And the ones for the, so 1 over R, this will be much below when R is bigger than LS than the string scale modes, which go like 1 over LS. Yeah? In this case right now, what I'm discussing, no. In general, when you do the coset constructions, Wess-Omino terms are important. I also didn't really have much time to talk about them, unfortunately. But for example, here I said you should find a regulator that respects symmetries and whatnot. So I'm explicitly saying I don't have any anomalous symmetries. For example, in the standard model, they play an important role if you want to integrate out one of the fermions, like the top quark or something like this. You know, the theory naively becomes anomalous, but it cannot be. So you're generating one of these Wess-Omino terms. So they play an important role, but right now for me they don't. So I can discuss it more in private, I guess. But yeah, but you need them in various settings. You need Wess-Omino terms. Okay, does this make sense so far? Okay, so this is the action, and as I explained, so you can get rid of both of these, and so it really starts at relatively high order, where you can, for example, have some intrinsic curvature squared, or you can also build it out of the extrinsic curvatures. And this means that this action is is universal if you compute predictions of that theory to a higher order than you naively would have expected. And we'll see this plays an important role for understanding why strings in 26 dimensions are special. So it's really the fact that you don't have a local operator at this order in 2 dimensions that makes this d minus 26 universal. Okay, so now that we have our theory, what we should try and do is compute predictions for it, and think about what the physical model is we're trying to describe. Before I do that, let me say a few words just about the theory, maybe, because they're interesting, I think. So let's consider the theory just for its own sake. So what we'll do is consider scattering amplitudes again for now. So a different way to motivate it is what I just said. So we eventually want to understand why 26 dimensions is special. So there's no 26 in the action. So it's not clear why a string in 26 dimensions would somehow be special, but you should be able to see this. And you would expect to see it at one loop, because it in various other ways shows up as the determinant, as the anomaly. So you should also be able to see it here at one loop. And what we can do is just compute scattering amplitudes to find this 26. And we'll also use them later for what we're actually interested in. So, and again, let's start at a tree level as a warm-up. So 2 to 2. And the action is over here, so we can just read off our vertices. One more comment maybe. So in 2 dimensions, the kinematics is very restrictive. So if you compute a scattering amplitude of P1 with flavor I, P2 with flavor J, going to a particle with P3 with flavor K, P4 with flavor L, then we can still write it in the way we did before. So this still has to be proportional to delta Ij, delta KL, and so on, to the SO d-2 invariant tensors. But the kinematics is so restrictive that the momenta are actually individually conserved, which means that either P3 is equal to P1 or P4 is equal to P1. And let me just for now always pick a P3 to be equal to P1. So, well, so this will always be taken to be equal to P1, and this one will always take to be equal to P2. So this is a peculiar thing of 2 dimensions. And then again, this will be A delta Ij delta KL plus B delta I K delta JL. And let me call this T. It'll be it's the transmission where they just pass through each other. And then R delta IL delta JK. And again, we only have to compute one of these guys if we want to compute the scattering amplitude. So we can compute A of S, T and U. And this is, again, we'll take I and J equal and K and L equal, but K and different from I. And so then the only diagrams we have is this guy. So plus, plus this guy. So 1, 2, 3, 4, 1, 2, and then here's 1 and 3 is contracted. And then here 1, 2, 1 is contracted with 4, and 2 is contracted with 3, and then we can work this out. Well, let's drop I've already dropped all the i's. So from the first one, and actually for the dimensions to come out right, there had to be some scale here, which I dropped, but there's ls squared here. So I get minus ls squared over 8. And then I have, for the first quantum, I have 4. For the second one, I have 2. So I get an 8. And then P1 dot P2, P3 dot P4 from the first diagram. And then for the next one, we only have 4 options. So the 4 exactly cancels this 4. And we get, and let me put the force like this, ls squared over 4. And this is 1 with 3. So this is t squared. And the last one gives ls squared over 4 u squared. So this is, and this one here, let me not write the whole thing again, but let me write this one as minus ls squared s squared over 4. Okay, so this is the tree level amplitude. And then let me just also record, because crossing is a little bit funny. So notice that I said I will take P1 equal to P3. This means actually that T is equal to 0 and U is minus S. So this means A is actually 0. The reason to keep it is that I can use crossing and don't have to compute T. So the crossed amplitude, I'm replacing T with S. So I have minus Ls squared over 4 T squared plus Ls squared over 4 S squared plus Ls squared over 4 U squared. And now T is equal to 0, U is equal to minus S, so I just get Ls squared S squared over 2. And the reflection amplitude is related to the annihilation amplitude, so this is 0. So these are the scattering amplitudes. So at this order, the only thing we have let me start over there again, I guess. Well, let me keep this. Any questions in the meantime? So at this order, our scattering amplitude only has the transmission piece. So we have delta, well, the delta I already pulled out, so we just have delta I k delta JL, and then Ls squared S squared over 2. And what you see is that this amplitude is now double soft in the momenta of these guys. This is something I wanted to show based on the current algebra exercises, but this is true in general. So amplitudes in this theory, if you take one particle soft, will always be go to 0 like p squared. And this is a consequence of the nonlinearly realized Lorentz symmetries. Okay, so this is the tree level piece, and now let's look at the one loop piece. And again, I can't do the one loop calculation in real time, but I can show you what diagrams contribute. So when you compute the annihilation amplitude at one loop, then this gets contributions from diagrams that look like this. Again, these are the flavors, so this will be proportional to d minus 2, and then you have to sprinkle the derivatives in the various places. So you have this one, and then you have this one, and you might have the other vertex over here. Then you have diagrams that go like 1 in the large d minus 2 counting. Again, you have to sprinkle the derivatives everywhere. You have the ones that look the other way. And then you have diagrams that look like this. I hope this is more or less clear. So you just, does it make sense? I mean, these are the kind of diagrams you will get when you do the calculation. Yeah? No, it's not. Yeah, it's excitations on the string. So we just have some two-dimensional field theory now, and you have phonons on the string. So you should think of it as having some long string. You make a little ripple over here, a little ripple over here. You send them in. And then this amplitude, what it tells you is that nothing much interesting happens. So let's say you have your string and you excite it like this, and you excite one guy down here in the one direction and the other one in the two direction, and you scatter them, they will just pass through each other. It will never happen that they reflect, and I'm not sure how to do that with my fingers, but this process will never happen. So they will always just pass through each other, and they acquire a phase shift. Okay, and so now let's look at the one loop amplitude. And the first thing is 1 over, so again, I'm doing everything in dimensional regularization because that's a regulator that respects all the symmetries. I mean, it's clear that you could have looked at a p-brane instead of a string, so I should have said all this construction isn't specific to a string, so this applies also for general p-branes. And then you could have thought maybe that somehow the divergent piece is absent, but this is not the case, and it's also no reason why that should be the case. You see the STU I didn't say, but this is exactly the structure you get from a term in the action from the intrinsic curvature, if you include this term. So you will generate, because we went away from 2 dimensions, this term is now physical, it's no longer a total derivative, and you have to include it. This is called an evanescent operator. You just generate a counter term here. I won't say too much about it, because once you go back to 2 dimensions, either t or u are always 0. And so it doesn't actually contribute at all in 2 dimensions, consistent again with the fact that this is a total derivative. But you would need it if you wanted to go to 2 loops, which we're not going to do. But if you wanted to go to 2 loops, you would have to keep this kind of thing in your calculation. So this is a divergent piece, and the fact that you can absorb it by this really means that by a local counter term in your action that respects all the symmetries means that your regulator also preserved the symmetry. So there's some non-trivial consistency check. If you were to use a different regulator, you can do this exercise with a Pauli-Villares regulator, for example. Then this is no longer true, and you have to add other pieces. So then let's write the finite piece, and most of it will be uninteresting, but there's one piece that is interesting. So there's, at this order, you get a contribution that looks like this, d minus 26 s cubed plus stu times stuff. Because this vanishes, even if I cross the amplitude, I will just not write the 0, so there's some 0 in here. This is not the 0. There's some stuff in here, but it multiplies 0. Then there's another piece, 12 tu t log s over t plus u log s over u. Now in the annihilation amplitude, this is still 0, but you see that it contributes when you exchange t and s. So it contributes to the transmission amplitude, to what I called t before. And it's good that it contributes there, because from the optical theorem we know that we need an imaginary part, and this is exactly what it contributes. So this, at the end of the day, in d equals 2, once you go back to d equals 2, absorb this guy. This is just minus ls squared d minus 26 over 192 pi s cubed. And then for t, I won't go through the algebra, but you can show that from here, if you put in you have to put back the I epsilons, so there's I epsilons here. You have to put them back in, and then you see when t is s that some of these pieces cancel and the other one give you an imaginary part. I ls to the 4 s cubed over 16, and we'll see the role of this in a second. So this is the amplitude, and you see how 26 appears in the language of these effective strings. And what happens physically now is that at one loop in the critical string, what I said is still true. So if you have a particle, one of these modes that's excited in the one direction, the other one in the two. No, let's do a different example. So we have two particles excited in the one direction, and what you can have when they scatter is that they come out excited in the two direction in any number other than 26. In 26, this will never happen. There's no annihilation. Things always pass through each other in 26 dimensions. From an effective field theorist's point of view, this seems very harmless. You just have some additional piece. From the point of view of two-dimensional field theories, it's actually a very big difference, because theories that are for massless particles that are reflectionless and don't have annihilations by crossing, they can be integrable, and it turns out that the string in the critical number of dimensions is actually integrable, while the strings away from the critical number of dimensions are not. So this really breaks integrability. Except, so I should say one comment. I didn't write out all the terms, but one case you might know, there's also a consistent string theory, which is in 3 dimensions, and you should see this from the amplitude. The way you see it is that you get s cubed plus t cubed plus u cubed if you only have one transverse dimension, which is also 0 in this 2-dimensional kinematics. So 3-dimensional strings also don't have any such contributions. Or strings propagating in 3-dimensional spacetimes don't have these contributions, and it's consistent with the fact that if you quantize it in light cone gauge, there cannot really be an anomaly because you only have one transverse direction, so you only have one generator that commutes with itself.
This one with amplitude actually some way like the argument is not clear to you apart from integrability how to relate this to the anomaly.
Yeah, it's not immediately clear from here. So one way to relate it to the anomaly, if you want, is if you quantize the string in a totally different way. You might start from the Polyakov action, integrate out around that background. You can integrate out the Liouville mode. You generate a piece that in the scattering amplitude gives rise exactly to this. So this, in that way, you can trace it to the one loop determinant, or to the. It's in that. So this was done by Polchinski and Strominger in that language, and so people usually call this a Polchinski-Strominger term. Okay. Any more questions? Okay. So what I wanted to do next is just an unrelated. Do I still have some time? Can I maybe also even do the QCD stuff in the discussion a little? I wanted to just do a brief detour on the critical string, because you will see some things looking familiar from what Juan was talking about. So I just briefly wanted to mention the analogies because we had a talk. Any more questions in the meantime? Okay, if not, so then let me make a comment about the critical string. And in that case, what you can show is that the S matrix is, yeah, well. So you get the momentum conserving delta functions, and then you have delta ik delta JL e to the I ls squared s over 4 exactly. So if you expand it out, you get this. Modulo, of course, you have to go from the normalization of states here to the normalization of physical states, which means you have to divide these things by a factor of 2s. And this means that so this is essentially the identity operator. There's also the crossed one, but and so this is the identity times e to the ILS squared s over 4. And this as a phase shift means that the scattering phase shift is just ls squared p1 dot p2 or s over 4. And this might remind you of the phase shift that was written down on the board for the scattering of shock waves in gravity. So you just have a phase shift that's proportional to the momenta of these guys. And this is not really a coincidence. So one way you can think about it, or you can make more analogies that make things look like the formulas we had in that case. What you can do in this theory, once you know the action, you can write down a classical solution. So let's find some classical solution. Let's excite one direction. I won't give it an index, but let's find one solution. Because these guys are massless, they will only depend on either sigma plus or sigma minus. Let me call it sigma plus. So, and then what this gives, you can compute the induced metric on the string in the presence of this solution. And the induced metric, or the line element, will be minus d sigma plus, d sigma minus, plus this classical solution prime of sigma plus squared d sigma plus squared, which looks a lot like the shockwave metric that we had. So it's not really a coincidence that the phase shifts are the same. And you can also, on the world sheet of the string, now look for a little probe. So you look at the space-time, this two-dimensional space-time with this metric, and then you scatter a probe. So you have some lump moving in this direction. Actually, probably now I'm giving it the wrong sign because I said I'll need it anyway. But and you can ask what happens if you have a probe particle. And if you do the calculation, you will find that it gets carried along with a bump. And you can compute the time delay for this, just like the calculation that was done. And you can also compute the time delay from this exact S matrix, and you find that the two are actually the same. So you can really compute all the things that were done in this little toy model, which was something we found amusing, I guess, at the time. We had a lot of fun with the model because you get to work with an exact S matrix and can see some funny features. So there's a lot more one can say just about this S matrix. I won't say a whole lot more, but I want to make maybe two more comments relevant to what we've been discussing. So one of the things that is interesting about massless S matrices is that they often describe RG flows between a UV CFT and an IR CFT in these 1+1 dimensional models, along the lines that David discussed in the first lecture. And the question is if this corresponds to a flow between a UV CFT and an IR CFT. The IR CFT, we know what it is. It's just D-2 free bosons. The question is there some UV CFT that controls this system? And the answer is obviously no from this phase shift, because what you need for a flow between a UV CFT and IR CFT is something where the left movers and right movers decouple both in the UV and in the IR, just because that's what you have to have in a two-dimensional field theory. And so what this means is that you might have the simplest S matrix where you can see this is an S matrix that looks like this, I m squared and then I m squared plus S. And this describes an interesting system. This is so this is scattering for a fermion. This is a Goldstino. And here you see both at low energies and at high energies, the left and right movers don't interact. So it becomes a CFT in the UV and the IR. And in the UV, this guy describes the tricritical Ising model. In the IR, it describes the Ising model. So this is a very nice paper by Samolochikov, if you want to read it. And the point to make here is that as you go to the UV, you see that the left and right movers never decouple. So there's no UV CFT that controls this system. Yeah?
Why do you
Well, don't you always have holomorphic in 1+1 dimensions? I don't know. David can maybe say more about this. I thought this was.
Yes, 5 times 5. It's not true that all CFTs couple into holomorphic and unbroken. No case. There is no notion of left current, right current, some path depending on speed, path depending on speed.
Okay, we can think about that.
Is not related to the Z and the R of the
Not directly. I mean. There's various other ways that you can see that you don't have a UV fixed point in this case. I mean, for example, I'll discuss it in a second, but you can write down the energy as a function of R on that circle, and you can get the central charge, or try to get the central charge in the UV and IR, and you see that if you go to small circles, which is where you would get the UV central charge from, you have a problem because of the tachyon. So, I mean, it just really, in many ways, is not controlled by a UV CFT. You can also see a lot of other funny behavior of string theory this way. So, for example, with this exact S matrix, you can scatter wave packets and try to see what you can actually resolve, what sizes you can resolve, and there's some minimal length in the system. And you're not surprised by it because it is a string theory at the end of the day, but you can just see it explicitly from the exact S matrix. So if you make wave packets for left movers, right movers, you scatter them, then they're always bigger than or equal than the string scale. So there's some uncertainty relation like this. Okay, there you can also see the Hagedorn behavior of string theory from this amplitude, etc. Okay, and so now what I want to do, I guess, is talk about the actual application and apply it to the QCD string. So, and for this, maybe let me take the thing down if I can. Yeah? I'm not sure. I mean, it is still two-dimensional. So, for example, we work at G string exactly equals 0, and the scattering in the two-dimensional theory is defined at all energies. The amplitude is well behaved. It's polynomially bounded on the physical sheet, and there's no issues, except it has some essential singularity at infinity, which encodes all the funny behavior. This one you said?
Yeah, that should do it.
Yeah, I still have some issue here too, but we'll see.
So what it does is
it
splits, so that's an entire separate screen.
Okay.
Setting to
Where am I? Where's my cursor? Ah, here we go. I mean, if I can just play it, that's also fine with me. All right. Okay, so maybe can we the middle light? Which one was the middle light? Was it this one? Yeah, I think that one. Yeah. Okay, so now let me get to the motivation why we got interested in this and why we started working out on effective field theory for it. And it's really based on the simulations, lattice simulations in Young-Mills theory. The simulations I'll mostly be talking about from Athenodoro, Bringolds, and Tepper. There's also some simulations by Morningstar and Cudi. And a lot of the things I'm saying, I mean, you could do to all the data sets. There's no really discrepancy or anything between the data sets. We're just using this one because it's the most recent. And so first let me discuss what you're seeing here. So what's shown here is the energy levels of closed flux tubes, and I'll say in a second exactly what's meant by this and how it's measured. But these are energy levels that they find as a function of the size of the object. So you get the energy as a function of the size of the object, and you see that the error bars are quite small. So it's actually good data, and it looks like you can learn some interesting things from it. So we thought one should try to find out how to describe it. And this one, obviously, is the ground state. It's the state with the lowest energy. Not all the other states have the same quantum number, so you shouldn't think of it as being some level crossing here. The red one, I'll discuss in some detail, is scalar under rotations around the string and is odd under parity, both in the direction along the string and parity across the plane containing the string. This one is a state which corresponds to one of these excitations moving around the string. So this has a spin around SO d-2 spin 1 and 1 unit of momentum. I mean, on the string, the momenta are quantized, so it has 1 unit of momentum. And you see exactly the 2 pi over r here. This is why it's rising. This one is a state that corresponds to 2 of these excitations, and it corresponds to a state in which the wave function for the guys is just the trace. So it's just the trace. So this is a scalar that's even under parity. And then this one, the one I'm showing here, is an excited state with 2 units of kk momentum, but still a spin 1. So you see there's a bunch of quantum numbers that they can measure, and there's really many more. I'm just showing some of the examples. Now let me briefly say what the measurement is in practice. So and I won't go into great detail, but I want to at least give you an idea what's being done. I can discuss it in more detail if there's interest. But so what is being done is you have your lattice, and I'll suppress 2 of the directions, and I'll just for now focus on the Euclidean time direction, and then this one I'll call x. So this is the direction along the string eventually. This one is the time direction. And then what is done here is that you have Polyakov loops, or a loop, a product of plaquettes that go around this. So these are compact, really. The lattice is compact. So these are all identified. So this is really a closed loop. And then you have the Hermitian adjoint over here. So what you're measuring is a correlation function of, let me call it p dagger of tau, p of 0. And the expectation value here really means you're summing over the realizations of your SU3 in 4 dimensions, pure glue. The way you would evaluate this, or one way to evaluate this, and just to insert identity here, and then you have the sum over all the states that have overlap with these guys. So 0 p dagger n e to the minus en tau. Okay. And we'll write this as just sum over n, Cn absolute value squared, e to the minus En tau. And if you separate them far enough, this is dominated by the lowest state that has overlap with these guys. And then you can do this for different sizes of your lattice. So this size is r, so this is the length of the string. So this is the measurement schematically that's being done. Does this make sense? And then in practice, it's a bit more complicated because this would be localized in the transverse directions, which would mean it's a superposition of states with different momenta. So what you're doing is you're really superimposing these things. So you're projecting onto the zero momentum state in the transverse directions. And you're also, anyway, so this, if you do this with a straight loop, then what you're getting is a measurement that you can do. Actually, and you get this kind of thing. It's fun to do yourself even, if you want the ground state. If you want to do excited states, it gets a little bit more tricky because if you use, in principle, they're contained in here. So if you have everything that has the right quantum numbers will appear in there. But it's a bit problematic because, of course, they're exponentially suppressed. So what you want to do in practice to measure other states is if you want to make loops that have a specific set of quantum numbers, and then you look for the lowest state in that sector. So, for example, so, for example, what you might want to do, now let's look at a different set of suppressed two different coordinates and look at so let this be now the thing along the string. So this is the x direction, and this is one of the transverse directions. What you might want to do is just give it a little bump like this, and then if you want to do something with spin 1, you take superpositions of this plus the one where it's pointing in the z direction plus the one in the minus y direction and the one in the z direction with appropriate phases to give it the spin you want. And this is how you would look at some of these kind of states. And then to look for this kind of state, this is the 0 minus minus state. What you could do is you could insert, if you're now in 3 dimensions, what you could do is you could take a loop. So this is now the direction along the string. This is y and z. You could take a loop that has a plaquette inserted in the YZ plane, for example. This has the right quantum numbers for this. And then in practice, if you just do these, it will not work. You won't have overlap with the states you're interested in because they're kind of low energy. These get, the more higher the resolution is, the worse it gets. So what you do is you kind of make them fuzzy by smearing them, blocking them, whatnot. So I won't go into details about this, but hopefully this gives you an idea what the measurement is. And then if there's questions, I can discuss it more. But this is really the basic idea behind these measurements. Does that make sense? Okay, and then now it's 12:05. So should I just continue later, or what's? I have a bunch more plots because I want to also just discuss the pseudoscalar that you know. So I want to just explain how we actually compute the predictions, because I haven't yet told you about the beta ansatz, thermodynamic beta ansatz. I haven't yet said. I think it's time.
So let's thank Raphael. Don't eat too much. We have a long afternoon.
I was pointing in the wrong direction with my question on the unbroken group. I mean the parameterization of the concepts.